Welcome to our lesson on the dual nature of light. Today, we are going to explore how light behaves like a wave in some situations, and like a stream of particles in others. Let us begin our exploration. Our learning targets today are very clear and focused. First, you will learn to describe how light travels and behaves using the wave model. Second, you will compare the wave and particle models to see how they explain different optical phenomena. Third, you will explain how photons are involved in the emission and absorption of light inside atoms. Think of these targets as a personal checklist for success in our lesson today. To guide our thinking today, we have the first essential question. How do wave and particle models explain light behavior in different situations? Keep this big question in mind as we analyze our observations. Let us start with a quick demonstration to challenge your brain. Look closely at this gray rectangle. Which side appears darker to you? Most people see the left side as darker and the right side as lighter. However, this is actually a visual illusion that challenges how your eyes perceive contrast. Think of it like a magic trick, where your eyes see a difference that does not exist in reality. The key point here is that we cannot always trust our first impressions of light. Here are two more optical illusions to test your visual perception. On the left, is that slanted line really broken? On the right, are the dashes on the tilted side really shorter than the horizontal ones? Although your eyes tell you that the line is broken and the dashes are unequal, they are actually perfectly straight and identical. Surrounding patterns can easily distort our vision. Look at these two puzzles at the bottom. Is the top hat taller than its brim is wide? Now, read the text inside the triangle. Most people think the hat is taller, and most read the sign as Paris in the spring. However, the hat height and brim width are identical, and the sign actually says Paris in the spring, repeating the word dia. Our brains make rapid assumptions. Take a look at this grid of black squares on the left, separated by white lines. Try to count the black dots that appear at the intersections of the white paths. You will find that as soon as you look directly at an intersection, the dark spot disappears, only to reappear in your peripheral vision. Let us look at one last illusion that makes perfectly parallel lines look completely crooked. On the right, look at the horizontal lines separating the rows of black and white tiles. Do they look crooked or slanted to you? It seems impossible, but every single horizontal line on this screen is perfectly straight and parallel to the others. The optical illusions we observed show that light does not always behave in ways we expect. Sometimes light appears to bend, fade, or form patterns that confuse our eyes. This leads to an important question. What is light really? To answer this, scientists use two models. In some situations, light behaves like a wave. In other situations, it behaves like tiny particles. Neither model works alone, but together they help explain how light behaves in different situations. When people hear the word wave, they often picture ocean waves or ripples on water. These are common and easy to see examples. Others may think of sound waves or even light waves. Music exists because of sound waves, and rainbows form because of light waves. Although these waves look very different, they all involve repeating motion that carries energy. This helps us connect everyday experiences to physics concepts. Let us write down the formal physical definition of a wave and explore mechanical waves. Let us define waves more precisely. A wave is a disturbance propagating through a material or a vacuum, carrying energy along with it from one point to another. 19. We classify waves into two major categories based on how they travel. Waves that strictly require a physical medium to propagate are called mechanical waves. This means they cannot exist without particles to vibrate, which is why we have sound, water ripples, tsunamis, and the physical vibrations on a guitar string. Imagine a wave traveling through a stadium crowd where people must be present to pass the wave along. Now let us look at the second type of waves, which are called electromagnetic waves. Unlike mechanical waves, these disturbances can travel through a vacuum, which is empty space without any matter. Examples of electromagnetic waves include visible light, microwaves, radio waves, infrared rays, ultraviolet rays, and X-rays. Think of starlight traveling millions of miles through cold, empty space to reach our eyes. The key point here is that electromagnetic waves do not require any physical medium to propagate. Let us focus on the nature of light and see how we classify things that produce light. Now let us examine the sources of light in our universe. The sun, stars, light bulbs, and hot, burning materials all share a common property that defines them. They produce and emit light. In physics, when an object produces its own light, it is called a luminous object. The sun is the most important luminous object for our planet, providing almost all of our natural light. While stars are also luminous, they are too far away to help us see at night. But what about objects that do not produce their own light, like the moon? On a clear moonless night, only a very small amount of light from distant stars reaches Earth, and it is usually not enough to see clearly. Objects like the moon and the planets may look bright, but they do not make their own light. Instead, they shine by reflecting light from the sun. Objects that do not produce their own light are called non-luminous. The moon looks bright only because sunlight bounces off its surface and into our eyes. Let us look at a specific category of luminous objects that produce light from extreme heat. For thousands of years, humans have relied on high temperatures to produce artificial light. When an object becomes hot enough to emit visible light, we say it is incandescent. Examples of incandescent sources include wood fires, candle flames, and traditional carbon filament lamps. Think of a metal poker left in a campfire until it glows bright red. The key point here is that incandescence is the emission of light caused directly by extreme heat. Now that we have reviewed waves, let us examine the main historical theories of light. We are now ready to examine the four major historical theories on the nature of light. First, the particle theory states that light consists of corpuscles that travel in straight lines. Second, the wave theory proposes that light behaves as a continuous wave. Third, the electromagnetic theory defines light as oscillating electric and magnetic fields. Finally, the photon theory unifies these ideas, stating that light energy is quantized. We will begin our historical investigation by diving into the 17th century with Isaac Newton. Toward the end of the 17th century, the scientific community began a great debate about what light is made of and how it travels. Sir Isaac Newton published his particle theory, which is the model stating that light consists of individual matter units. Newton argued that light is composed of corpuscles traveling at extremely high speeds. He believed that this model was the best way to explain how light travels in straight lines and bounces off mirrors. Think of throwing a stream of microscopic tennis balls that bounce off a flat wall. Newton used his immense prestige to promote this particle model, which became the dominant scientific view for more than 100 years. In 1666, Newton conducted a groundbreaking experiment by boring a small hole in his window shutter to let in a single beam of sunlight. He passed this sunlight through a prism, which is a transparent triangular tool that separates light into its component colors. To his amazement, the white sunlight spread out into a beautiful spectrum of colors on the opposite wall. People previously believed that the glass itself added the color to the white light. Think of a prism acting like a sorting machine that separates a mixed crowd of people into single-file color lines. Newton proved that colors are already inside the light, waiting to be revealed. In 1704, Newton published Optics, which became a foundational text in physical optics. Physical optics is the study of the properties and behavior of light. In 1690, at the same time Newton was promoting particles, Christian Huygens proposed a wave model. Huygens concluded that light is actually a longitudinal wave, which is a wave whose particles vibrate parallel to its travel direction. He argued that light waves propagate in all directions at a constant velocity through a hypothetical, weightless medium called ether. Importantly, Huygens was the first to suggest that each color of light has a different wavelength. Think of ripples spreading outward in all directions when you drop a stone into a quiet pond. This wave theory offered a powerful alternative explanation, even though most scientists initially ignored it. Throughout the 18th century, the scientific community was deeply divided over the nature of light. Because of the massive prestige of Isaac Newton, the majority of physicists strongly favored his particle theory. They believed that waves could not explain why light travels in straight lines without bending around obstacles. However, this consensus began to crumble at the start of the 19th century. Scientists began discovering new phenomena that could not be explained by particles under any circumstances. In 1801, Thomas Young designed an experiment that shattered Newton's particle theory of light. He passed a beam of light through a single slit, then through two closely spaced parallel slits, and watched the pattern on a screen. If light were made of particles, you would expect to see two bright lines corresponding to the slits. Instead, Young observed a complex pattern of alternating bright and dark bands. He realized that this behavior could only be explained if light acts as a wave that spreads out. By proving this wave behavior, Young single-handedly resurrected Huygens' wave theory of light. Young explained that his double-slit pattern was caused by wave interference. As light passed through the two slits, it created expanding wavefronts that overlapped in space. Where waves met in step, they created bright bands, but where they met out of step, they canceled. Think of two people jumping in a pool, creating overlapping ripples that grow larger or disappear. The key point here is that interference is unique to waves. Even though waves were confirmed, scientists still did not know what was actually waving until the 1860s. In the 1860s, Scottish physicist James Clerk Maxwell achieved one of the greatest unifications in physics history. He brought together electricity, magnetism, and optics under a single mathematical framework. Maxwell demonstrated that light is actually an electromagnetic wave, which is a transverse wave consisting of oscillating electric and magnetic fields. These fields travel together through space, constantly regenerating each other at the speed of light. This meant that light does not need a physical medium like ether to travel. Maxwell's equations revealed that visible light is not unique, but is part of the electromagnetic spectrum. The electromagnetic spectrum is the entire range of electromagnetic radiation, organized by frequency and wavelength. All of these waves travel at the speed of light in a vacuum, but they span an enormous range of frequencies. This spectrum includes low-frequency radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Humans can only see a tiny portion of this spectrum with our naked eyes. We can divide this vast spectrum into two major categories, based on how they interact with matter. To understand the health effects of light, we must classify radiation into two categories based on photon energy. The first is non-ionizing radiation, which is low-energy light that cannot remove electrons from atoms. This includes radio waves, microwaves, infrared, and visible light, which are generally safe at low exposure. The second is ionizing radiation, which is high-energy light that can remove electrons from atoms. Ultraviolet, X-rays, and gamma rays are ionizing and can alter molecules, damaging living cells and DNA. Think of non-ionizing waves as gentle ripples on a lake, while ionizing waves are like high-speed bullets that break structures apart. The boundary between these two types is a critical safety concept in modern medicine and technology. We often assume that our view of the world is the only one, but nature is full of invisible signals. While humans cannot see near ultraviolet light, which is high-energy light just beyond visible violet, many animals can. Scientists conducted experiments with the red-winged parrot to study this behavior. They discovered that female parrots use ultraviolet patterns on male feathers to choose their mates. These beautiful markings are completely invisible to humans but highly vibrant to birds. At the start of the 20th century, classical wave theory could not explain how light transfers energy to matter. To solve this mystery, Albert Einstein proposed the photon theory of light in 1905. This model, also known as the quantum theory of light, suggests that light is composed of photons. A photon is a discrete packet of electromagnetic energy. Einstein built on Max Planck's earlier research on blackbody radiation to argue that light energy is divided into fixed packets. This was a revolutionary departure from the idea of light as a continuous, smooth wave. Max Planck was a German theoretical physicist who originated quantum theory, winning the Nobel Prize in 1918. Quantum theory is the study of matter and energy at the atomic and subatomic levels. The photon theory shows that light carries energy in packets. Each photon carries energy proportional to its frequency, calculated using the equation E equals hf. Here, h is Planck's constant, or 6.626 times 10 to the negative 34th joule seconds. It is a fundamental constant relating a photon's energy to its frequency. Photons have no mass and no electric charge, but they do carry momentum and travel at the speed of light in vacuum, which is 3.00 times 10 to the 8th power meters per second. Imagine photons as tiny envelopes of energy traveling through a vacuum. The key point here is that light energy is divided into distinct packets. In 2024, researchers in Birmingham achieved a historic milestone by creating the first image of a photon. They captured this lemon-shaped particle of light as it was emitted from the surface of a nanoparticle. A nanoparticle is a microscopic particle with dimensions under 100 nanometers. Imagine actually seeing a single packet of light that was once considered invisible. Now let us look at how researchers have recently succeeded in visualizing these individual particles of light. The photon theory helps explain atomic spectra, which are the patterns of light emitted or absorbed by atoms. In this model, light consists of packets of energy called photons. When an electron absorbs energy, it jumps to a higher energy level, creating an absorption effect. When the electron returns to a lower energy level, it releases energy as a photon. This produces bright lines in an emission spectrum. Because each element has a unique set of energy levels, the emitted light forms a specific pattern of spectral lines. These patterns act like fingerprints for elements and are used in fields such as astronomy and chemistry to identify substances. When atoms emit or absorb light, they produce specific spectral lines based on their energy levels. Because each element has a unique arrangement of electrons, each one produces a distinct pattern of wavelengths. In the image, hydrogen, helium, sodium, and calcium each show different sets of colored lines across the visible spectrum. These patterns are studied using spectrometers, which separate light into its component wavelengths. Scientists use this technique in many fields, including astronomy, chemistry, and physics. A famous example is helium, which was first identified in the spectrum of sunlight before it was discovered on Earth. By examining the precise wavelengths emitted or absorbed, astronomers and chemists can identify unknown substances. Imagine using a barcode scanner to identify products in a grocery store. Spectrometers allow us to analyze materials from great distances, including distant stars. How do the wave and particle models of light explain its behavior? The wave model explains how light reflects, refracts, diffracts, and interferes by treating light as a continuous disturbance. The particle model explains how light transfers energy in discrete packets, especially during atomic interactions. Before you leave class today, please complete your exit ticket. First, name one theory of light and state its key idea. Next, explain the difference between mechanical and electromagnetic waves. Finally, identify which part of the electromagnetic spectrum is visible to human eyes.